Okay, we are live. Here we go. Um, so, welcome to my stream. My name is Kent Quirk. I am a software engineer. I've been doing this for some 40 years and still have a lot to learn. I've been doing Advent of Code problems live in Go for a couple of weeks now. We are at day 19. Yesterday was day 18. I did a 2-hour stream, which didn't solve the problem. And frankly, I kind of over-engineered it. I had a desire to. So the problem was basically a expression parser with some unusual constraints that you can't just like copy paste from a standard library without understanding how it works. and So they basically just played with precedence in a normal sort of add and multiply expression parser. And I tried to do it with just an explicit expression structure, like, trying to recursive descent parser. And that's finicky and hard to get right. And I wasn't thinking about it as clearly as maybe I should have. So eventually I ended the stream because it was getting long. And went back to it today, tried to wrap that up and decided it was just a bad idea. And really what I should have done is what I have almost always done in the past in that situation, which was use a parser generator. So parser generators are programs that write programs. In particular, the types of programs they write are parsers for languages. So you specify the structure of the language using like a standard form, and then you run this generator and it writes code that parses that language. So I decided to do it that way. Now, not going to spend a lot of time giving a long lesson on parsers, but essentially, like the earliest parser generators, there's one called Yak, which is the most popular. I'm not sure it was the first one, but it was because it's called yet another compiler. It is a generator of compilers. And the thing about Yak was that it was what's called LR1 parser, which means some specific things that I won't go into. And then later on, people have come up with other expression grammars that are a little easier to deal with, a little easier to work with. And so instead of having a separate tokenizer and parser, you could just have a parser that understood how the tokens are broken up and how the language is broken up, and you kind of express things that way. And the most common of those these days is called a PEG parser. Parser expression grammar, I think, is what PEG stands for. And there are a lot of variants of PEG parsers, and there are a couple of different libraries of PEG parsers in Go. Now, in the past, I have used one called Pigeon, but Pigeon is getting a little old and hasn't been updated in a couple of years, so I thought it would be a good idea to try a new one. So I jumped on and I used something called PEG. And downloaded it, and this is what a PEG grammar looks like. So notice it's not colorized because I don't have a PEG grammar smart in the editor, but essentially what it says is E is an expression which is space, which is an optional amount of spaces, followed by an E1 and then the end of the file. And then an E1 can be either an add, which one is this? This is A. In either an add or a multiply. Now in this language, add and multiply had the same precedence. So this was easy to do, is say E1 is either an E2 added to an E2 or multiplied by an E2. And then we did an E2 because I wasn't sure if we were going to need negative numbers in the second half, so I threw in negative number handling as well. And then you just parse, the values are numbers, which is what this is. And then we have add, minus, multiply, open and close, and spaces. So this, when you run the parser generator, generates this file, which is not meant for reading by humans, but it knows how to parse that language. And then the structure of the parser is that you construct one of these, you initialize it, and then you call parse on the expression that you pass in and execute it, and then you evaluate it. I don't know why there are so many steps. Other parser generators I've used haven't had as many steps, but I didn't bother to investigate it further. This worked. So I wrote this little grammar and it parsed part 1 properly, and then and gave me the right answer. And then part 2 said, okay, now you're going to do a different grammar. There's going to be precedence in the grammar. And so in this case, the grammar needed the thing that I didn't put in the first time, which is that multiply is stronger. Add is stronger than multiply. So multiply can do these, but add binds tighter. And so if you were doing My Dear Aunt Sally, you would flip these two. Add would be first and multiply would be second. But in this case, we just reversed multiply and add, and then everything worked. Now, the thing that was weird about it was because this is Go, and because Go doesn't like putting, well, in this case, the grammar generator is not, can't be shared. You can't have the same grammar generator generating 2 versions of the grammar for use in the same program. So I couldn't make one program that used both of these parsers without putting them into sublibraries. And it was just easier to just duplicate the library and create 18A and 18B. So if you look at my source code on GitHub, I haven't been showing this. I'm so sorry. I'm just going to go back and show you the code for the grammar. Here's the PEG grammar that we've been looking at here, that we've been talking about. So add and multiply are in the same group here, and then in the other one, multiply and add are in separate groups, separate levels of the dependency structure. So that multiply can be made up of a bunch of adds, and the adds are binding tighter than multiply. If you were asking multiply to bind tighter than adds, you would flip these two. Anyway, so in the end, this worked, got the right result, and it's on my GitHub under Kent Quirk. So feel free to check that out. And now we're going to move on to today. Now, because yesterday took me so long, and I was a little nervous about how long today would be, I did peek at today's problem to try and think about it a little bit first to make sure that I had an approach I wanted to use before I spent all my time and all of your time going over this, especially since I wanted to go over yesterday's as well. So here we go. We have a this is a expression matching. This is basically, can you build regexes? And if you've been watching me, you see that I've always liked regexes. I kind of enjoy working with them, and they're sort of fun for me to think about. This is straight out of regex 101 kind of class in terms of how these machines work. And I am not going to recreate regex processing. I am going to leverage the language's support for it. So they give us a file that that has a set of rules, and actually the file has a set of rules and then a set of strings. And what we are going to do is we want to know which of these strings conform to rule 0. But a rule is not quite recursively defined. Well, it is recursively defined, but there's no infinite recursion. So rule 0 consists of rule 4 followed by rule 1 followed by rule 5. Rule 4 is this rule, just the letter A. Rule 5 is the letter B, and rule 1 is either rule 2 followed by rule 3 or rule 3 followed by rule 2. Rule 2 is either 2 4s or 2 5s, which is 2 A's or 2 B's. Rule 3 is 4 5 or 5 4. So anyway, what we are going to do is, and our job is to say which of these rules conform, they match the rule, which of these strings match the regular expression rule. So the way we're going to handle this is that we're going to build a regular expression out of this. So we're going to take rule 0, which is the rule that we're trying to evaluate, and we're going to take it and we're going to substitute, where we see a 4, we're going to substitute in rule 4, which is A. When we see a 1, we're going to substitute in rule 1, which is this. When we see a 5, we're going to substitute in rule the B. And then we're going to loop on that until we have no numbers left. Because they say in our instructions that that there are no infinite recursions and that we're always going to resolve this down to just A's and B's. So in the end, we're going to have this big string that is a set of A's and B's, and then we can hand that to a regular expression pattern matcher. We can ask Go to compile it as a regular expression, and then we just walk through these strings and say, does it match or not? So that's the thing I want to follow. So our job here is split this file into 2 pieces by the blank line. Then parse the first part into a collection of numbered rules, and parse the second part into, and then have the second part as the collection of strings. So then we just count the ones that match. No big deal, hopefully. Hopefully. So let's see if we can actually do that. So I've already set up day 19. So we're reading the input file. We're going to do an input sample. And we are going to so this splits it up by lines. Yeah, you know what? I'm just going to pass. I'm going to have a func build rules, which is going to take lines, which is a slice of string, and it is going to return. So our rules are going to be a map of int to string. And so rules is make map int string, and then we're going to do for line in lines, and we want to break as soon as we see a new line, as soon as we see a blank line. So if line is quote break. So great. So now we're going to read through all these lines, and we have a number at the beginning of the line, a colon, space, and then a string of things that we're going to replace. So all we're going to do is do a strings.split on colon space. So let's do index and contents is strings.split of line quote colon space. And then n comma s. So now we have a number, and then we can say rules of n. Actually, I don't even need to convert these to ints. I can do map of string to string. And so then I don't need to do this. And then I'm going to call this ix again. Rules of ix equals contents. And that's fine. So that's going to build me a set of rules, and then we just need to return it. Return rules. Okay. So rules is build rules lines. Let's just make sure that we got what we think we got. Input sample.text. Somebody doesn't like something. Oh, I need a range lines. Range lines. And wait, strings.split is returns a list of strings. Okay. Slice of string. So all right, let's try that. All right, now it's happy. Go run main.go. And that's saying, okay, map of 0 is 415, 1 is 2332, 2. So that worked. So we got what we were looking for. Now, all right, because we want to substitute these in groups and we want to make sure that nesting is preserved, the way these are defined, we can put a parentheses around these. So 2 can be parentheses 44, vertical bar 55, close paren. And then when we substitute in, we'll substitute in other matching sets of parentheses. So we can just wrapper all of these lines. So instead of saying rules of that is contents, what we can do is instead we can say it's left paren plus contents plus right paren. And then that's going to let us substitute in with all the nesting in parentheses preserved, and then we can clean it up when we're all done. So, great. Now we have that. So we're going to do a function substitute, which is going to take a string and rules, which is a map of string to string, and it's going to return a string after substituting in all of the values we're talking about. So, and then we're going to call this repeatedly. So we're going to pass in this string. I'm going to say, look, we have a string here. And now we're going to take this string, and we're going to take the numbers out of it. Because what we're going to be doing is, as we replace, so we replace the 4, we're going to replace the 4 with paren, quote A, quote, paren. And the 5 is going to be replaced with that with B. And the 1 is going to be replaced by another bunch of numbers inside parens. And then we're going to call it again. And, you know what, I'm going to just do it in a loop. And then just return the final thing. So basically we're going to iterate over this thing until there's no numbers left to substitute. And then all we're going to have is a big collection of A's and B's with a lot of noise around them, with parentheses. And then we can eliminate the redundant parentheses and call this a finished gig. So call that a pattern. So let's substitute... we're going to do this forever and return when we're done. Okay, so we have S, and we need a pattern. No, what we want to do is pull out all the numbers. So we're going to take and make a regular expression that just extracts the numbers from the string. So let's do numpat is, we're going to do a split, or regular expression split, where what you specify with regular expression split is the things you don't want. So what are the separators? So we are going to say it's regex dot must compile, and the string we must compile consists of not 0 through 9 and some number of those characters. Oh wait, does this work? So we are looking for, we're looking for groups of non-numeric characters as separators. Because those are the things we're going to match. We're going to have when we're done. So if we give it this, you know, paren 2 3 3 2, we're going to get 2 3 3 and 2 out. And we want runs of more than one of those if we can. Well, at least one. Yeah. So we must compile that, and then we are going to do splits is the numpat dot split of S, and we want all of them. So all of the so we're going to end up with a bunch of strings, and we might end up with some of these things at the beginning and the end, which means that split is going to leave some noise. It's possible that these strings will have not only possible, like guaranteed, because we have parentheses in these things now, the ends of these strings, these strings is going to have a blank both at the beginning and the end of our splits array. I am going to take this to... No. Isn't that? I can't do that in one shot. Splits equal splits from 1 up to length of splits minus 1. So that way we're getting rid of the two things on the ends, because we know that when we call splits on the contents of the rule, that there is the rule is going to have parentheses on both ends of it. So this just saves us a little grief. So now what we have is a set of strings which are all numbers. And then we can do 4, comma, split in range splits. I guess actually I didn't even need to do that. I could just do that this way here. We'll split it here because we don't have to keep it around. So so now for each one of those, we're going to substitute for it and we're going to have duplicates. We really want that to be a map. I mean, a set. It may get tedious. We're going to substitute in rather than, I could put these in a map and then range over the map. Make map string struct. So this is the idiom for a set in Go. And then here we're going to say replacements split equal struct. So now we have replacements instead of splits. So the replacements thing is just a set of the things we are going to replace with no duplicates. We have just eliminated the duplicates with this, which is going to allow us to do a replace on our strings only once for each string. So that just saved us a little bit of iteration time, and probably if we print something for debugging, we'll need to do that. So so now we have a set of replacements. Now we're going to take our string that we just went to replace. So now we're going to say so we're going to replace like all the 4s in the string with the value we have with the element 4. The thing we have to be careful of is, if you look at this, input.text has a lot of replacements. It has 135 of them. So if we just replaced 10, then we would also end up the 107s would be replaced by whatever was 10. So we can't do that without matching the edges of our replacement. So what we have to do is we have to do a smart replacement that says replace only whole numbers. So what we want to do is say we're going to make a regular expression out of the number, the string that we have, with boundaries on it. So we're saying replace the number 10, but only if it occurs without other stuff on the sides of it. So we're going to look up in Go regexp, and I think we want word. So yes, this is what I want. B. We want B. Okay. So we are going to say replacement pattern is regexp dot must compile, and now we're going to say backslash B. You know what? I'm going to do this in using Go's raw string format or whatever they call it, so that I don't have to deal with extra backslashes. So it's B. We're going to put that B plus. Oh, I have to iterate over the list of replacements. So for REPL range replacements, so B plus REPL plus backslash B. So now we're going to, that's our replacement pattern. We're going to find the things that start and end with our replacement. I mean, where it's a replacement as a whole word. And now we can say S, or yeah, S is going to become REPL pat, nope, not find string, dot replace all string and S, why isn't it? Replace all string source. Replace all string returns a copy of source, replacing matches of the regular expression with the replacement string REPL. So, yes, the replacement string for REPL is rules. REPL. And when we have done that, we're going to go back and do it again. And we're going to keep doing it until we have replaced, until there are no replacements left. So the question is, all right, so we just made this, and so the question is how many replacements are in this list? So we can say, if length of replacements, why did it do that? Replacements is 0, break. And then when we're done, return S. I'm gonna fly by the seat of my pants. I'm gonna try this. So we have the rules. We print the rules. We then say S is substitute of rules of 0 rules. And so this is either going to loop forever or it's going to do something. It did something, and it even worked. Look at that. Okay, so now we have A, or BB, AB, BA, AB, BA, AA, BB. Okay, so we've got some ors in it. Now, there are a bunch of spaces, quotes, and parens in this thing that we don't need. So we want to match. We want to clean this up before we return from substitute. So what we'd like this to be is to eliminate everything that looks like quote, paren a quote, and replace it with an A. Everything in replace it looks like quote, B, replace it with a B, and we can get rid of all the spaces. In fact, we have to get rid of all the spaces. So let's do, there's a nice little feature called, so replacer is a strings.new replacer, which takes, we want to replace, we'll use these funky raw strings, and we're going to say we're going to replace quote A ding with A. We're going to replace, we're going to do that same thing with B. And then we're also going to take spaces and replace them with that. And then we can just say, oh, we don't have to say return S here. We can't say return S here because we're not done yet. So S equal, or return replacer dot replace of S. And now that gives us a pattern, which is, so our matching strings have to start with an A and then with a B and have this stuff in the middle. And now we just, so our day, so now we have our, we have a, pattern, which is that thing. Our reg expression is that. And we are going to, let's say println day 19a, and 19a is going to take our reg expression and our now, you know what, I have a feeling they're gonna probably change the rules on us somewhere along the way. So let's go here. Func day 19a takes lines as an array of string and returns an int as usual. And now we are going to move this code And so now we're going to say, so now we have a thing that looks like a pattern. And we need to count the number of lines in this file that match the pattern. So we can actually iterate over everything because who cares? Because all those other lines aren't going to match. So it may be a little redundant, but I don't care. For underscore comma lines. So so our pattern now is a regexp. I'm going to do must compile and let it panic if it fails. Our pattern looks just like that. So regexpression expression. So now I have a pattern is compiled. Oh, wait a minute. We don't want to match part of a line. We need to wrap the pattern in let's do it here. A new line, beginning of a line, plus our regular expression plus a $sign. So we needed to remember too that this pattern has to match the entire thing, not just part of it. So we're saying caret meaning beginning of pattern, $sign meaning end. So for line and lines, count is 0, count plus equals pat dot match string line, and then return count, and that's that. So for our sample data, they say we should have 2 matches. So been forgetting that lately. If count plus. That's what we wanted. Two. It worked. We think it worked. Let's do input instead. $124. Okay, that was a hell of a pattern. Look at that. That's big. But we got a plausible number, so let's put it in. That is the right answer. Yay, part 2. All right, matching rules aren't quite right. Completely replace rules 42. Oh God. Okay, so this is a recursive rule set now. They specifically told us it wasn't going to be or it wasn't recursive, and then they went and said, "Oh, never mind, it actually is." So 42 or 42.8, 42.31 or 42.11.31. So what this works out to in a real pattern is stars. You can have some number of stars. So 42 or 42.8 means Rule 8 is preceded by an arbitrary number of 42s. Do we believe that? So it says Rule 8. Yeah, Rule 8 can be preceded by an arbitrary number of 42s. Rule 11 can be preceded by an arbitrary number of 42s and followed by an arbitrary number of 31s. No, that's wrong. Rule 11, yes, no, that is correct. Rule 8 is either 142 or okay. So the question becomes, how do we put that in here? So when we look at Rule 42, oh, good grief. Yeah, no. Rule 42 is just a thing. So our substitute everything in rule is now going to fail because we can just iterate on this forever. Because Rule 8 has an 8 in it, Rule 11 has an 11 in it. So So when we see 42 or 42, whoa, my browser just arbitrarily crashed. Thanks, Safari. That was fun. It's probably because something happened on Twitch. Kind of hoping it didn't kill my stream, but looks like the stream is still going, so okay, great. All right, so they've given us a smaller input sample that does this. So let's first create that input sample. input sample 2, and we are going to copy this. All right. So let's start to see if we agree with this. We should get 3 if we run this on input sample 2. Great. So the thing we need to substitute, though, is that for updating rules 8 and 11 here, rule 11 is 4231 or 421131. So it really becomes 42 plus 31 plus 11. That's what the rule really is right now. And oh, wait. All right, this is even easier than I thought it was. Okay. Rule 8 is an arbitrary number of 42s, and Rule 11 is an arbitrary number of 42s followed, one or more 42s followed by one or more 31s. And Rule 8 is one or more 42s. That's all there is to it. So they want us to do the rule recursively, but we could just make it so that Rule 11 gets a plus on it. Or instead of phrasing it the way they have, if we did this as a plus here and a plus here, and we did Rule 8 as a plus here, then we just have to get those pluses through our substitution process. We have to not eliminate the pluses as we parse this thing. So if I were to do that for input sample 2 and main.go so we build the rules, we're splitting out our replacements, have to compile that. I'm not sure we have to change anything else. This could be a lot easier than I thought it was. Well, let's just, for giggles, what happens if we do that? Son of a gun, it worked. Where's the plus? Here's a plus here. And here's a plus here. Oh man, I love having the insight. It said now total 12 messages match. So if we were to just, let's modify input.text to have that. And rule 42, and 8 is 42 plus. And rule 11 is 42 plus 31 plus, and rerun it with input.text. $241. Oh, dang. Okay. Did I just do it wrong? Hold on. What? So, input sample 2. Rule 8 is 42 plus. Rule 11 is 42 plus 31 plus. Input.text. 42 plus 31 plus. Oh, wow. Wait, so where is... It's 42 plus. Rule 11 is 42 plus 31 plus. Why didn't this work? Alright, so... It did work for our first case, so what could be wrong here? Alright, so... Anyway, there's almost 400 lines. How many messages completely match rule 0? Now it's interesting that rule 0 is, in fact, 811. So, rule 0 is rule 8 is 42 plus. So, an arbitrary number of repetitions of 42. Rule 42. And then 11. Oh, eek. This is worse. No, it says Do we need a star instead of a plus? Hold on. This is bad from the point of view of because this is 8 and 11 and rule 8 is 42 and rule 11 is also 42, and now we have an arbitrary number of them. We should match anything more than 1. We should match 2 or more. As long as the thing starts with 2 or more repetitions of 42, then we'll be good. But in fact, what we have here, because that should work. Oh no, because what's going to happen is the 8 rule is going to consume all of the 42s. And then 11's not going to have any left. So if we do, I want to do a simple test of this. Let's go to our Go file, and we can say, before we do anything else, we can say so let's do A plus B plus, and our input string is going to be AB, and we want to know if this matches. False. This does not match, which is actually correct. But if we do that, does that match? True. Does match. Okay, so let's just look at this again. 8 Okay, 42. Eight can be 42. And then so if we say, just for giggles, that 42 is, let's do a let's do a just a quick test thing here. So if we say 0 is 8 followed by 11, and we say 8 is a or a 8, and we say 11 is a b or a 11b, then you can have as you have to have at least one A, but you can have an arbitrary number of them. And then that's followed by a similarly arbitrary number of A's, followed by an equal number of B's. Ooh. So it's not just so wait, how would I write this as a regular expression? Because this is counting. Because yeah, that's the thing that's different now, is that A11B means that there have to be basically an equal number of A's and B's, preceded by some other, so they have to be a little more A's than B's, is kind of how it works. And so I can't just say arbitrary repetitions. I have to do nesting. This is this is weird. Okay. This is just evil. The set of So this is not an easy... I mean, I think to solve this, I'm actually curious as to whether Python's regular expression system could solve this better than Go's. So the thing that's interesting is Go does not allow recursion in regular expressions, or look ahead or look behind, because those things can cause regular expressions to blow up infinitely and to take ridiculously long times to process. So Parser regular expressions and the way they're often implemented in many languages, it's possible to write pathological regular expressions that can essentially take, close to forever or take enormous amounts of memory to process. And Go specifically chose an implementation that didn't permit that, but it also doesn't permit certain advanced regular expression things like look behind and look ahead. This, and possibly the concept of self-referential regular expressions, which I think might be allowed by some languages. Let's just take a look at the Python one for a minute. Python 3 reg expressions specials. Back reference to a named group. It matches whatever text was matched by the earlier group name. So no, I don't think you can do a named group that contains itself, which is what we're after here. So I think this just can't be done this way. And so it means that we have to think about this problem somewhat differently. What's annoying is that their demo 2 works the way that it happens to match. They didn't put any counterexamples in that wouldn't do it that wouldn't work this way. And I don't know whether that was evil or just lucky. I'll assume lucky. Although this stuff like this, the constructing these things is a huge challenge, and my hat's off to the people who do it. And by the way, I have thrown them some money, and if you're enjoying this, maybe you should think about doing that too. So I am going to, we could certainly explode it's rule 11 that is our problem. So who else uses 11? Only at the top level. So we could solve for we could add an extra test where we figure out what it is that Rule 11 actually means. like we do our replacements over all the rules, and then take a look at what we have when we're done. Let's do that, because that might give us a solution that isn't terrible. So we build our rules. So let's do day 19b. And what we are going to do here is I'm going to revert my input.text to remove the plus signs. And sample also. And then I can overwrite them in code instead after parsing it. So, input.text. Now that's fine. Input sample, I didn't change at all. Main.go. So in 19b, we build the rules, and then what we're going to do is we're going to say rules 8 equals um, 42 plus rules 11. So I'm just going to put my rules back in that I had a minute ago. 42 plus 31 plus and then if we do everything the same, then we should get the same answers. We should get the answers that we expected. Let's remove let's comment out these prints for a bit, just to reduce the noise. Yeah, so that's the same answers we thought we had, but we're wrong. So now what happens if instead of just doing substitutive rules of 0, what if we substituted all the rules? This is going to be kind of ugly. We're just going to try this and see what we get. Wait a minute. That's not at all what I thought was going to happen. Oh, rules 2. You know what? Instead of doing println of rules, let's do so we're going to do each one in a new line, and it's going to be dump. It's going to be a massive dump, but that's okay. So what did 42 end up being? Here it is. 42 is this god-awful mess. And 31 is this. So if I were to use those and count the number of repetitions of 42 at the start of the string and the number of repetitions of 11 at the end of the string, as long as in rule 0. Alright, so yeah, let's do that. So let's put this back to this. Now we'll just comment these out. We're not going to modify them. And I don't need to do this. I can just say rule 42 is substitute rules 42 rules. And the same for rule 11 or 31. Oh, but actually, Pat 42. The only thing I don't care about the end. I only care about the beginning. And Rule 31, I only care about the end. And now, oh, nope. Since rules are surrounded by parentheses, I can say star S. So it's Rule 31, or plus S. How many, as long as there's at least one of those, how many are there? Oh, actually it's worse than this. So, here's my thing. I want to say, does the string have Pat 42 at the beginning and Pat 31 at the end? And then I want to know how many copies of Pat 42 at the beginning does it have? And since they may vary in length, I basically have to iterate through trimming them off. I have to match caret Rule 42, delete it, and iterate through that. Keep doing that until I have reached the end of the setup. So we're going to strip the beginning. So so we have to do it. I don't need this anymore. Let's do these. We have all this. So we're doing for range of lines. But instead of, so it's, what we're going to say is while, or for pat match string align, pat 42. Oh, no, it's not match, because match, no, it contains any match of the regular expression. The regular expression has a caret at the beginning. So if the then we are going to, so count 42, count 31, count 42. So we found a match, and now we say pat 42 dot replace is there a replace string? I guess it's replace all is fine, since it's anchored to the beginning of the string. So replace all string, and the source string in this case is our line. line equals, and the replacement string is empty. And so that works great, right? And now we do that and replace that. And oh, and I still need a count. Count. So if Pat 31 is less than Pat 42, strictly less, then count not Pat 31. Count, these are both count 31. So what if we run this 19b on input sample 2? Ideally this should 3 variables with 1 values. Now it says 15 match. And then actually, no, this one still needs to be line. That's the reason I did that. Okay. So what the hell? Why'd it get stuck? S. Oh, it's stupid. Okay, strings dot has prefix of a or strings dot has prefix b. If we don't have either of those as prefix, continue, so that we skip all the crap at the beginning. Can 42 match an empty string? Can't possibly match an empty string. So oh, how did I do that and not? Okay, that's better. All right. So I can get rid of these now. Do this again. So it says there's 0 42s, but 3. Oh no, 0. Yeah. I'm gonna swap these two because they're confusing me. 42. So 3 and 0. So since they're count 31. Ah, okay. If count 31 is greater than or equal to 1, and says 14 now. Let's only print the ones that matched. So 5 of those. Followed by one of those, and actually it says that the result is nil, which it has to be, because and 2, 14 and 3, 18 and 4, 23 and 5, 25 and 6, 27 and 7. 45, wait. 45 and 12. See, the problem is the 45 and 12 should not be valid, because the requirement is that there be nothing between them. So if S is not equal to quote quote, and so now this should say, oh, sorry, if S is equal to quote quote, this should say 13, which is still wrong. So which one have I got that I shouldn't have? Looks like this one I shouldn't have. No, this one they have. No, we both have it. This one, oh, I have to reset my counts, that's all. These don't... These have to go inside the loop. I think this will work now. $12. Okay. Now, what happens if we do this on input.text? I may regret this printout, but let's see. No, it's not so bad. What number did I use before? 241. Does that seem right? I don't remember what number I entered before. Well, I'm going to say it looks plausible. Let's try it. 241. 241. Shoot. curious. What happens if I do S there? So it looks like do we ever have more than one? We never have more than one match for path 31. I am... Alright, let's go back to input sample 2. Take a look again. We only ever have one match for... Just gonna do that again just so I can see it better. Out of curiosity, if I were to reverse these two, and then, so I get the same answer for input.text, so I get the same answer for input sample 2.text. I mean, it still gets the same answer. Okay, So my code is consistent. And I'm about to hit 2 hours, so I'm gonna stop. I'll look at it in the morning, think about it later. And I hate like hell to do this, but I'm just done for tonight. So, yeah. So, once again, we learned the lesson of maybe it's sometimes just good to sleep on it. This went really well at the beginning. I thought it was very cool, very quick. Steam felt good, and then boom. You get thrown a monkey wrench into the problem, and you have to really think about it hard. And I mean, let me just say, it happens in engineering all the time. You get your requirements, you go to build your product, and then somebody comes along with a new requirement that just blows your design out of the water. I mean, maybe it doesn't blow the whole design out of the water, but there's something that happens that comes up that's real, and you have to cope with it. And this is the reason that software rots over time. Like, I mean, nobody's probably still watching this, but I'm going to say it anyway. Software rots because the environment in which the software lives has changed. And that's the requirements, that's the customers, that's the hardware, that's the software environment, that's a security patch, whatever it might be. All of a sudden, your platform provider has decided that something you used to do is no longer valid, and they prevent you from doing it, and you have to re-engineer. And now, it's like, oh, well, I don't have time to go back or, it's like it would be a bad idea to go back and re-architect the whole product. You patch and you hack and you flip some bits and you make things work, and, and then you find out eventually the thing start to fall over under its own load. And that's just life. So, anyway, take care, good luck, and I will see you tomorrow. Bye.